Now we are going to talk about missing and sensor data. When you look at the textbooks and examples, statistical examples, in the textbooks, the data look nice. All data are there. Data sets are small, nice. But when you go to the real life and get experiments, sometimes data are either missing or you don't have time to wait till end of experiment, and some data turn out to be censored. For dealing with missing and censored data, you really want to be a Bayesian statistician. So let's start with missing data. The missing data would have this taxonomy proposed by Don Rubin, which is distinguishing three types of missingness. MCAR, MR, and MNAR. We are going then to talk about multiple imputations as a method to deal with missing data and see how WinBugs implement these multiple imputations. So the taxonomy of missingness is having, as I said, three different types of missingness. MCAR is missingness completely at random. That one is described when the datum is missing, but missingness does not really depend on either observed or unobserved data. It is simply completely at random. Missingness at random, MAR, may depend on the observed data. So particular datum is missing, the missingness may depend on the other data that you observed. Now these two, MCAR and MR, are easy to deal with, but the MNAR is the difficult one. That missingness is essentially when the datum is missing because of its own value. It is missing because that datum influences missingness. And it is quite difficult to deal with missingness which is not at random. We are going to see a couple examples. The first two, missingness completely at random and missingness at random, are called ignorable missingness. Ignorable because you can easily deal with this kind of missingness. MNAR, missingness not at random, is non-ignorable missingness. If you impute the missing data using some statistical model and you have single imputation, that could be misleading because you impute the data look like complete, you perform the inference, but the estimation of the error is not correct because you really did not account for uncertainty of the imputed data. To alleviate that, Don Rubin suggested so-called multiple imputations. So you have data, Y denoted, in which you have part of it observed and part of it missing. And what you do, you impute multiple observations here. And in terms of inference, there are three things that are distinguishable in multiple imputation. The first one is how to find actual posterior distribution of data, given observed data. Well, you can essentially average complete posterior distributions completed by imputation. Also, how to find the posterior mean of data given observation. You can average repeated complete data posterior means of data. Finally, what is the variance of your parameter given the observation? That would be average of repeated complete data variances of data and plus the variance of repeated complete data posterior means of data. So here we have the data, which datum Y. We have part of it to be observed, part of it to be missing, and then we impute 1, 2, up to M different missing values and get the M copies of complete data. From each complete data set, we find the estimator of the parameter, and then we average all the estimators, and that's how the multiple imputation works. In the Bayesian fashion, the multiple imputation is straightforward. You essentially simulate as many as you have the simulations that you ask your MCMC to do, M of those, and you simulate from the posterior distribution, from the data that you already observed, not with respect to missing data. And then you simulate the missing data from the likelihood in which you plugged in the value for posterior mean for theta I. That is automatic in WinBugs. You simply denote missing data by not available, NA, these data are treated as parameters, and they would be simulated by from the model automatically, given the current value of the parameters data, which are coming from the posterior. To illustrate that, we are going to go through 3 examples. We are going to have rats example, which is one that we discussed earlier. It is the very first example in the set of examples provided by OpenBugs and WinBugs. In this one, we have ignorable, in which some y's or responses are missing, and that's easy to handle. Then we will have the rats ignorable 2, in which some x's are missing. That is a little bit more difficult if you have predictors missing, and also some y's. And then we have version 3, in which we have informative missingness. In this case, the y is missing depending on its size. This is non-ignorable missingness. How you achieve that? For 1, you do nothing. You essentially assume that these missing y's are not available. WinBugs will take care about those automatically. In 2, you will need to put statistical model on x's, some random design. And given this random design, these missing x's would be generated. And finally, in 3, you really have to know very well your experiment. It is really not a statistical problem. You have to know why in this experiment or in this data collection, particular datum is missing, maybe depending on its size, maybe depending on some other feature of the very missing datum. In here, we dealt with missing data in which missingness depends on size. So for example, we will say that missingness of datum I is Bernoulli, and this Bernoulli would have some probability pi. So the data would be missing at random with probability pi, but then the logit of pi would depend on this missing datum itself. So it would be some, for example, linear regression a plus b times yi, where yi is the missing datum. And then we can put some priors on the parameters a and b. We can adjust these priors in such a way that we can, for example, regulate that missingness is depending on size, and for example, when datum increases by unit size, then it is going to be missing 1% more, and that kind of thing. So for this one, you really have to know very well the mechanism of missing data to set some model how data are missing.